First, just for reference, I have solved this differential equation using our Chapter 3 methodology, where I find the characteristic polynomial, find the roots, and then build the solution from that. So I acknowledge that there is an established way to solve this differential equation. I just want to use this as an example to demonstrate an alternative way that could not only be applied to this differential equation, but could be applied to a whole host of other differential equations as well. And this method relies on making a substitution of variables so that my dependent variable is no longer y. And this is how that plays out. I start by defining x1 to be the dependent variable y. And then my second dependent variable x2 I define to be y prime. Right off the bat, that gives me now an equation in terms of x1 and x2 that feels like the type of equation we've encountered in the systems that we've been solving recently. Specifically, I'll be able to write x1 prime equals x2, because clearly x1 prime will just be y prime, which I have chosen to be x2. These substitutions so far are completely generic. They have nothing to do with my actual differential equation. So what I'll do next is I'll define x2 prime in a way that captures the relationship that's being defined by my differential equation. Notice in my differential equation, y double prime equals 6y prime plus 7y. Using these variable substitutions, I could rewrite x2 prime, which would be equal to y double prime, as 6 times x2, which is my stand-in for y prime, plus 7 times x1. Then these two equations that I've underlined here in green comprise exactly the type of system that we've been solving in previous examples. Here, let me rewrite that a little bit more explicitly. So this system is equivalent to the second order differential equation that I started with in this problem. I'm going to go through the steps of solving this system pretty quickly because this is, again, exactly the type of problem that we've encountered in recent examples. What I do want to emphasize about this problem is this substitution method. And you could actually imagine if I had a y double prime term, I could continue making substitutions to account for all of the higher derivatives. And so, in fact, any LHCC differential equation of any order can be transformed into a corresponding or equivalent system of first order linear differential equations. So now I will simply solve this system using the eigenvalue eigenvector techniques that we've demonstrated recently and verify that the solution that I get is equivalent to the solution that I would get using my Chapter 3 techniques. So let's go ahead and work through the steps of solving this system. And I, of course, solve by finding the eigenvalues and eigenvectors of the coefficient matrix A. And here I've worked through those steps. And then one interesting thing that I want to point out real quick before I build my general solution is that this quadratic, which we solve in order to find the eigenvalues of the matrix, we have referred to as the characteristic polynomial. And if we scroll up and look at the work I did previously using our Chapter 3 methodology, you see that the polynomial that we solved in that method matches the characteristic polynomial of this coefficient matrix exactly. And that is not a coincidence. If we set up a system of linear equations, linear differential equations, using this protocol, this sort of recipe or strategy for converting an LHCC differential equation into a system, then it will always be true that the characteristic polynomial of the coefficient matrix in that system will match the characteristic polynomial that we would have got using our Chapter 3 technique. So anyways, I just think that's kind of an interesting feature there. Looking at the work I did, again, I believe that this is getting familiar to us, and so I solve that characteristic polynomial to get eigenvalues. I plug those in. I've got the corresponding eigenvectors, so I'm ready to build my general solution. So this is the general solution that I would get in terms of the vector matrix methodology that we've used here. And then just to verify that this matches the solution that I got earlier, let me go ahead and write out the two separate solutions that are represented in this vector form. And these are those two solutions. And then I'll remind myself that x1 was defined to be y, and x2 is defined to be y prime. And so my solution should be this y equation. And if I look back to what I did a second ago, this y equation does match that solution that I derived using the previous methodology, with one small exception. Because of the choice, the way I've chosen to represent this eigenvector, notice that this coefficient here is negative. Well, technically, this C1 is some arbitrary value. And so if I had initial conditions and I plugged them in and found a certain C1 value, this negative would sort of get absorbed into that constant coefficient value. So in a certain sense, I could think of this as being either positive or negative, since it is, in fact, just an arbitrary constant, an unspecified unknown constant, which could be either positive or negative. Note that since x2 has been defined to be y prime, then the derivative of this term the original term here and its derivative do have to have opposite signs. So hopefully this detail makes sense, but I argue that this is in fact equivalent to the solution that I found a second ago. And if I really wanted to make it look exactly like that, remember that any scalar multiple of an eigenvector is also an eigenvector. So I could have chosen to write this eta eigenvector as 1, -1, and then these coefficients would have been reversed in sign. Anyways, like I said, I claim that it is in fact the same solution. This derivative agrees, and so this method gives me an equivalent answer to the methodology that we used previously. And as I pointed out, it's probably more efficient. It's certainly more efficient in this particular case to use the other methodology, but this technique that we've just demonstrated can be applied in a pretty wide variety of cases. So there are examples of differential equations which can be more efficiently solved using this matrix representation. In the next example, the final example for this section, we're going to demonstrate an application of systems of first order linear homogeneous differential equations, and this is an extension of an application that we saw earlier in the semester. Let's take a look at that example. In this final example, we revisit a context that we investigated early in the semester, but we've added kind of an extra layer of complexity here that will require us to use a system of differential equations to model what's going on. Essentially, we have a solid, in this case salt, being mixed with water. You may remember this type of problem from earlier in the semester. The detail here that has changed is that we now have 3 tanks. Specifically, we have the mixture from the first tank flowing into the second tank, where the mixture is, the solution is then mixed again, and then that resulting mixture flows into tank 3. Here's a rough sketch of kind of the setup here. I've got some liquid entering tank 1. We're actually told that pure water flows into tank 1. So that mixture, the liquid coming in is pure water. In tank 1, there is some initial amount of salt mixed in with the water. Once that mixture is thoroughly mixed, it gets passed into tank 2. Notice that tank 2 and tank 3 we are told to assume that they initially contain only water. So initially tank 2 and tank 3 contain entirely water. Tank 1's got some salt in it, and some pure water is being poured in. That mixes with the salt water that's already in tank 1. That mixture gets passed on to tank 2, which mixes thoroughly and then gets passed on to tank 3. And then it finally passes out of tank 3 as our final output. So our goal is differential equations, eventually equations, functions, which describe exactly how much salt is present in each tank for a given time t. I've started by adding a few more details to my picture. Let me just explain. First of all, we're told that the flow rate of pure water is exactly 10 gallons per minute into tank 1. And then the rate of flow of liquid between each of the tanks and then eventually out of tank 3 all have that same value of 10 gallons per minute. So I've labeled that on my picture. In addition, because that flow rate is constant coming into each tank and out of each tank, the actual amount of liquid, the volume of liquid in each tank will remain constant. And we're told what those volumes are. Tank 1 has a volume of 20 gallons, tank 2 40, tank 3 50 gallons. So I just labeled those on my picture. And again, the dependent variable that we're trying to model here is x sub whatever the name of the tank is. So x sub 1 will be how much salt is in the tank. And notice again that this is the amount of salt. So this is the actual number of pounds of salt. Just as a case in point to clarify what I mean, we're told that tank 1 initially has 15 pounds of salt. So that will directly translate into an initial condition for the x1 variable. I know that x1 of 0 equals 15. In the parentheses here, we're told that the other two tanks initially contain only water. That is to say, they contain no salt. So translating those into initial conditions, I know that x2 equals 0 because that's the amount of salt in the tank at time 0. And the same will be true for x3 for the third tank, since it also starts out with 0 salt at time 0. Next, we need to set up equations which describe the rate at which the amount of salt is changing with respect to time in each of the tanks. These will, of course, be differential equations because we'll be describing the derivative of x1, x2, x3, because we know that derivative captures the rate of change that we're after. Let me actually start with tank 3. So let me start by setting up an equation for x3 prime. So how fast, let's think about tank 3. How much salt is in tank 3 and how is that amount of salt changing with respect to time? Well, initially, as we've already pointed out, tank 3 has no salt in it at all. And again, remember I'm talking about the amount of salt. So I've already established that through this initial condition. So then how does tank 3 ever have salt in it? Well, clearly salt is introduced into tank 3 through the salt that's leaving tank 2. At the same time, though, we assume that the mixture is sort of instantaneously like a perfect solution, and then some salt leaves tank 3. So to account for both of these factors, I'll have to find the rate at which salt is entering tank 3, and then subtract the rate at which salt is leaving tank 3. So how fast is the salt leaving from tank 3? Well, we know that at any given moment, the amount of salt in tank 3 is given by x3. That's just how we've defined the variable x3. So x3 captures the amount of salt. Well, all of that salt is not leaving all at the same time. In fact, the amount of salt, the rate at which salt leaves is proportional to the rate at which the liquid is actually leaving this tank. So we know that the liquid is leaving at a rate of 10 gallons per minute out of the 50 gallons that exist in the tank. So this fraction accounts for the rate at which salt, the proportion of salt that's leaving this tank. So we'll multiply that fraction by the amount of salt that's in the tank at any given moment, and that should indicate the rate at which salt is leaving the tank. At the same time, as we've pointed out, salt is entering the tank from tank 2, and it is entering at a rate given by this expression here. The liquid is entering at a rate of 10 gallons per minute. The concentration of salt in tank 2 is given by the amount of salt in tank 2 divided by the total volume of liquid in tank 2. And so this overall expression here counts the rate at which salt is leaving tank 2, and therefore the rate at which the salt is entering tank 3. Applying that same reasoning to the other two tanks, I get these equations for x1 prime and x2 prime. Let's take a look. x1 prime, well, the amount of salt entering tank 1 is 0 because the liquid that's entering tank 1 is pure water. So x1 prime should be purely negative because there is only salt leaving tank 1. The concentration of salt at any given moment in tank 1 is x1 divided by 20 because there are x1 pounds of salt at any given moment out of the 20 total gallons present in X1 and tank 1. That concentration is leaving at a rate of 10 gallons per minute. Again, applying the same reasoning, I get this equation for X2 prime, and the structure of this system now looks very similar to the systems that we've been dealing with in previous examples. So let me go ahead and write this in vector and matrix form, and then we can work through the steps to find our solution. So just translating the system that we just built into the matrix vector form, this is the way the problem now looks. And as I mentioned, this is exactly the type of problem that we have solved recently. And so we should be able to work through the steps pretty efficiently. Let me go ahead and crank through the necessary calculations. So here I solved for my characteristic polynomial. You'll notice that the characteristic polynomial is just the product of these diagonal entries, which implies that the eigenvalues will be the diagonal entries of my original matrix. And that's not a coincidence. That doesn't always happen, but that does happen when there are zeros above or below the diagonal of a matrix. It's a property that we would say this matrix is triangular, and so all of those zeros there just make all of the determinants kind of go away. And so that's a property that you may see in a linear algebra class or may see proved there. For this particular example, I'm just pointing it out because it's a convenient result. And then for the sake of time and space, I have just sort of stated the eigenvalue, eigenvector pairs, and I haven't worked through all the details, but that's a process that we're quite familiar with now. So now I have all of my eigenvalues and the corresponding eigenvectors. So this is my general solution, and just one detail that I'll point out before I actually plug in my initial conditions. I'm not surprised that all of these exponentials have negative coefficients in the exponent, because given the structure of the problem, I expect the amount of salt in each tank to eventually just approach zero. Remember that we're starting with some initial amount of salt in tank 1, but then pure water is getting pumped into tank 1. So eventually I expect the amount of salt in each tank to just go to zero. And that will certainly be true given that all of these exponentials are vanishing as t grows without bound. So plugging in that initial condition, I get my coefficients turn out to be 5, 30, and 125, and then putting those in to my general solution, I get this actual solution down here. I ran out of space, which probably doesn't surprise you, but this gives me my actual solution. And then if I wanted to, again, I could sort of parse out the individual solutions. So if I look, for example, at the first row, I see that x sub 1 is simply 15 e to the negative 0.5 t. Now if you think about the structure of that function will start at 15 at t equals 0 and then simply decrease exponentially. And given the context, that makes perfect sense. The amount of salt in the first tank is initially 15 pounds, but then strictly decreases after that since pure water is pumped in. If I look at x2, I see that x2 has a negative exponential term as well as a positive exponential term. And so those will sort of counteract each other so that initially for small t values, this function, this x2 function, will increase. But then eventually the sort of vanishing exponentials will take over and that solution will head to zero. The same is true for x sub 3. And so you could graph those three individual functions and you would see that the relationships that we would expect are in fact modeled by these specific solutions. So in this last example, I just wanted to demonstrate one application. There are lots and lots of applications, but I just wanted to show this one for now, and we'll encounter a few others as we move forward in this chapter. But that wraps up section 5.7.